All right. So this talk is going to focus on sort of further and sort of a little more complicated aspects of RMG, sort of focusing a little more on sort of running RMG a little bit more efficiently, avoiding challenges related to memory, and also handling those species selection errors that we kind of glossed over a little bit before. So first, most of these things are related to the model block in your RMG input files. Um, so this is kind of where you add these features and these options in. So first we're going to talk about the speed and memory limitations. What's important to understand is that RMG in general has three primary, oh, I should get my laser pointer out, speed limiting operations. How fast it can react species, how fast it can run pressure dependent calculations, and how fast it can simulate the ordinary differential equation. In practice, RMG usually this effectively causes RMG to have primarily two scaling regimes. Early in the run, when the core is small, RMG tends to be limited by how fast it can generate all possible reactions, due to the number of isomorphisms required, and also by how fast it can run pressure-dependent calculations if you're running with pressure dependence. However, later in the run, when the core is very, very large, the ODE simulation starts to take longer. And we start to be limited by how fast the ODE system can run its simulation and select the species. When you transition between these regimes in your RMG run is highly system dependent. So it's I can't give you an exact number because it depends heavily on what kind of chemistry you're doing. Now, one of the first ways that you can work towards speeding up RMG is by running it in parallel. And RMG can run essentially reaction generation in parallel if you add this option when you run RMG. And this, if you're running with about 6 processes, this can get you about a good factor of 2 speed up earlier in the run in that regime where reaction is limiting. It's hard to get a little bit more than this because this process is going to saturate. And this isn't going to be too much help later in the run when the ODE simulation is limiting. So you're parallelizing an operation, but not the limiting operation in the late parts of the RMG run. Another way to look at it is adding species constraints to your model generation process. And this essentially works, so this is a separate block for the model block. And this essentially works by letting you set a maximum number of carbon, oxygen, nitrogen atoms, or radical electrons that species can have in your mechanism. And this can considerably help. It can let RMG sort of skip over some of these more complicated structures and species with lots of radical electrons that can be more difficult to deal with. This also avoids the larger species that have that generate more reactions than smaller species. But you do need to know that you do run the risk of filtering out species that you can't, that are actually important in these runs. And so you need some degree of a priori knowledge of what's going to be important in the system to know that you can cut it off at a certain point. Otherwise, you're going to suffer from some mechanism truncation error. Another way to speed up generation of reactions is by using filtering. Nominally, what RMG does without filtering is it just takes everything in the core and reacts everything in the core with everything else and generates all of those reactions and then adds everything that gets generated to the edge. However, what filtering does is essentially we estimate the maximum rate coefficient that these different reactions, bimolecular, unimolecular, trimolecular reactions can go. And based on that maximum rate coefficient, we say, well, if these two, without reacting these two species or this species, how fast do we think this could be? And if this flux was less than the your flux tolerance times the characteristic rate, then you would say, well, then this is pretty unlikely to be important, because even if it's as fast as we think it possibly can be, we still don't think it's going to be fast enough to move past the flux criterion. And so this allows RMG to skip reacting on species unless their concentrations get high enough that these fluxes are large. This is very robust, and it's highly recommended in gas phase. So it's highly recommended that you just put this. I would just always include this if you're running in gas phase, and probably liquid as well. We don't have this implemented for surface, so you can't do this on surface. Um, yeah. Another way that's more on this kind of the big regime end where your ODE's limited is you can use the RMS based reactors. So these three are the original sort of RMG based reactors. These are RMS based reactors. It's also not that too hard to add new RMS based reactors. It's designed for you to be able to do it relatively easily, but it does involve going into the code. This can get you maybe a factor of 2, factor of 3 speed up, but of course, again, this is only going to be in the late simulation limited regime. And now to talk a little more about memory limiting errors. So within a computer, your random access memory is, speaking a little bit roughly, is the amount of memory that your computer can sort of hold at once in a way that's efficient for it to run computations on. This is distinct from disk space, storage size, or how much memory can be stored within your computer. And so when RMG is running, all of the objects that RMG is dealing with, all the species and reactions, have to be stored in this random access memory for it to be efficient. And really here we're thinking about the edge size, and the edge is much larger than the number of core species. It's also important to think in this about the edge scaling with core size, which is pretty consistent between different types of chemistry, but can be very different between different types of chemistry. Now, the problem is that if you get a whole lot of edge species and edge reactions that take up lots and lots of memory, and you get above your random access memory, then what will happen is either the run will crash or everything will get very, very, very slow. And this becomes a problem in a lot of these very large models. And you can see kind of in this graph over here, as we increase our number of core species, how much the memory consumption increases. And our main way to deal with this, we at least call pruning, which removes unimportant edge species and reactions, which decreases them, which essentially attempts to cap the memory consumption of the RMG run. In particular, flex ratio, flex-based pruning, and then also we have thermodynamic-based pruning algorithms. So before we get into pruning, how RMG sort of usually operates here is according to this graph. So each of these, our y-axis here is the flux ratio. It's the edge species flux to an edge species divided by the characteristic flux. Each of these lines represents a different edge species that we're tracking the flux of. And this conversion is broadly the progress in the RMG run. And so usually with no pruning, one might have the tolerance move to core and the tolerance interrupt simulation to be the same thing. So that once you find something that you want to move to core, you stop the simulation, you add it to core and restart the simulation. And so as you can see here, we run the simulation, we track the fluxes of these, and then when this one reaches the tolerance move to core and tolerance interrupt simulation, then we stop the run. We start over and add that species and then react species. Now, within flex pruning, we add some additional parameters. First is tolerance keep in edge. And we say that if an edge species flux ratio doesn't exceed our set tolerance for all times during a simulation, the edge species will be deleted. we're starting to look a little bit more at this tolerance interrupt simulation, which before in this setup, having it be further out doesn't help us that much. But in this case, it makes a huge difference because we want to complete this simulation. We want to know that the edge species flex ratio doesn't just increase later on and become important, because otherwise we'd be removing it. If we were removing it here early in the run, we'd have trouble, because if it was actually important over here, then we've missed it completely and we'd have some species selection error. So we want to put this interrupt tolerance very high, so that we can go complete a simulation and do this analysis. And also we set a maximum number of edge species, so that when a simulation completes, if the number of edge species exceeds our set number that we want to keep our cap around, it will remove edge species with the lowest flex ratio until it achieves this maximum edge species. So now when we look at this plot, it looks a little bit different. We've increased our tolerance interrupt simulation quite a bit. So now if we track these, we have these different edge species, and as you can see here, these ones increase. We have a couple that go over the tolerance move to core, but none of them go over the tolerance interrupt simulation. So we do make it all the way through the simulation, but we have one that never goes above the tolerance keep in edge, and that's an edge species that we can prune, that the algorithm will be allowed to prune. So nominally, we have our tolerance move to core and tolerance interrupt simulation. In this case, we changed this to do pruning. We're going to increase this a whole lot, so maybe to a really, really big number like 1E8 to try and ensure that we run the whole simulation through. And then we're going to set a tolerance keep in edge. The general rule of thumb is to put it about 1/10 of the tolerance move to core. We're going to set some maximum edge species. Usually this is the default, I believe, is 100,000. But what you set it to may be dependent on how much random RAM you have in your computer. And then min core size to prune is the size of the core at which the RMG algorithm is allowed to start pruning edge species. And then min species exist iterations for prune is how many iterations an edge species has to be in the edge before it's allowed to be pruned. And as you can see here, this makes a really significant difference in these RMG runs. As you can see here, we've essentially capped our memory. And as a result, we're able to run out much farther since we don't crash, and we're able to build a model that is closer to the experiment here. Now, thermodynamic pruning is an alternative algorithm. And this tries to remove species that have really high Gibbs free energies of formation and are therefore not very stable. And it does this by computing this Gibbs ratio. So you take the Gibbs free energy of your given species and subtract the Gibbs free energy from the maximum core Gibbs free energy, and divide by the difference between the maximum Gibbs free energy in the core and the minimum Gibbs free energy in the core. And anything that has a Gibbs ratio higher than this, higher than some set tolerance, gets removed. And also maximum edge species is maintained in this manner. Usually 0.1 to 1 is the range of parameters you might use for this. And then the other parameters are mostly the same as the other pruning. It's important to understand that thermodynamic pruning is is more of a emergency option. It's primarily for cases where the flex pruning is not keeping the memory under control enough. Because unlike the flex pruning, which has a lot of rules about how it's tracking the edge flexes and being careful about not removing stuff, the thermodynamic pruning can guarantee you edge size, which can help you control the memory better. But this algorithm is significantly less safe than flex-based pruning. Any questions on pruning before we continue?
Do you know if it's currently working with pressure dependence? I think it is, but There was a while it wasn't.
Um, I thought it was, but I
I assume
haven't
it
heard
is.
anything recently. So,
Maybe it was 10 years ago it was broken, but okay, I'll assume it's working.
um, but certainly those two have some interesting interactions. Certainly. Um, all right. So next we're going to talk about species selection and pathway pickup problems, and this part is focused on species selection errors that we had been mentioned earlier, but we didn't go into too much detail. So most of the time when you're running RMG and it misses some species that you want it to have, it's due to poor thermochemistry and rate estimates. This is almost always the case. When generating a model, your first few iterations should really be focused on refining those parameters to get this stuff right. However, there are some species pickup challenges where RMG might will miss certain pathways because of sort of broader algorithmic aspects. Um, and that's what this section is going to be about. So first, we're gonna talk about a couple sort of main classes of these species selection errors, sources for these species selection errors. Primarily one class is primarily these feedback loop based processes, and another one is sort of focused on when you're dealing with a chemical system that has molecular weight growth. So to go a little bit, get a little bit cerebral, and sort of, so imagine we have some chemical system, and we have some A, and this A goes to B, which goes to B, D, which goes to E. But suppose there's an edge reaction, that would go from B to C, and there's some edge reaction that would go from C to Q. And suppose Q is somewhat special, in that it's essentially a catalyst. And if we had Q around, then Q makes a really, really efficient pathway from A to E. The A can go directly to E that will be way faster than this main pathway here. In this case, you can then in this case, Q is an incredibly important species. Q would have whether we include Q or not is going to completely change how accurate our mechanism is. However, we run into the problem of, well, how do we detect Q? And we have a huge problem here because if Q could be important if Q is a really, really good catalyst, it could be important at relatively low concentrations. This doesn't have to be high flux to make this pathway important. And more particularly, we don't even know Q exists. Q isn't even in the Q here isn't actually in the edge because C is one step out. C isn't in the core. So there's not really a way, it's not just RMG's algorithm. There is no numerical way to detect Q from our core edge system here to detect that this is the case. Because we don't know that this flux is important. So if Q is important to arbiter, the only way that we can find Q is by simply just keep lowering and lowering and lowering our flux criterion in the hope that eventually it comes in. But Q may have enormous importance despite having a relatively low flux. Now, fortunately, this is a very theoretical problem. So in most cases, you're not going to run into a system like this, where this is arbitrarily small. But it is common to run into cases where there is a path somewhat like this that has an appreciable flux, but a much smaller flux than sort of your main pathways. And this is an important thing to consider. And this can be like radical generating pathways can have this effect, somewhat of this effect. However, they are a little bit more detectable than you could claim theoretically could be the case. So another little more realistic problem is suppose we're running RMG. And we have species A and species B in the core here. Now, when we simulate when we simulate this system, if we just have A and B in the core, this blue line is the edge flux of B to C or B to D, assuming these two have the exact same rate coefficient, which reaches about 1 at time 5. Now, if we add B and C into the core, because this flux is so large, we add B and C, suddenly the flux from B to D drops to this orange line, about an order of magnitude drop in flux. And the green line, and if we add B to D in, it drops even further down to here. And this in a certain sense gets at a sort of a fundamental challenge with handling with the RMG expansion process, that it's very dependent on flux buildup. And what's really sort of happening here is you're going to have a lot of this buildup here, which builds up to a really high flux, when in reality, the concentration of B is never going to be as high as it is here, because it's going to go through onto C and D in the real system. But what this also suggests is that which one of these we add first changes whether we're going to add the other one or not, at least in terms of the flux criterion that we've talked about the most about so far. In general, this problem tends to happen in what it gets its name from the case where you're following a pathway of a radical. And the radical, and where the RMG will tend to build a pathway for that radical, but it won't include all of the side pathways. And because it's not including a lot of these side pathways because of this flux drop from blue to orange, what will tend to happen is that the radical concentration will get much, much higher here than it should be, because it doesn't have these reactions that are taking it away. And this can have a very significant impact on mechanism predictions in radically driven systems. And now kind of the more a very realistic and a little bit more grounded challenge that's a little bit related to the orphan radical problem, a little bit related to the catalyst problem, which is the chain branching problem. So in a low temperature combustion chemistry, you have this common, there are these key important feedback loops that control and drive the increase in the radical concentration, particularly the highly reactive OH radical. And these feedback loops form by somewhat doing a little bit of molecular weight growth on the fuel. Here we have our fuel, we get our N-propyl radical here for propane. We add an oxygen, the oxygen reaches over and pulls a radical off. We add an oxygen to that side, and then this oxygen reaches over, takes a hydrogen, and we lose an OH, which makes this ketohydroperoxide, which then decomposes to make two OHs. And so we've started with one radical, and we've made 3 radicals. And so these heavily drive radical production in these low temperature combustion regimes. However, initially, RMG isn't going to have this whole pathway. And RMG has a significant difficulty picking up these pathways because while they aren't tiny flux, they're significantly smaller flux than these main pathways. And so often RMG will won't be able to find these simply because they're maybe between an order and 2 orders of magnitude smaller than sort of these main fluxes. However, these are incredibly important because they control the radical concentration, which controls how fast everything happens in that regime. So I'm going to talk about 3 different ways to sort of work towards mitigating these problems. So I'm starting with the simplest and getting more complex. The first is you could simply add multiple species at a time. And this comes a little bit from here about well, okay, why don't we just add C and D at the same time? And this can help in some cases by allowing RMG to add kind of all of the important branches at once. This does tend to increase the model size at constant tolerance, though, but you can set this maximum objects per iter, the sum integer like 5. I wouldn't go much past 10 usually, but 5 is usually okay. and then tell it to terminate at max objects if you're not using flex pruning. This essentially tells it because you're going to need to increase your interrupt tolerance a little bit because you want it to go a little bit further out to collect more than one species. Now we're going to get towards something a little bit more complicated. And this is called the branching algorithm. So RMG's flex criterion, if we look at some species I that has some concentration or reaction mechanism, and it has some production flux that's producing it and some loss flux that's consuming it. Now, RMG's flex criterion focuses heavily on both this loss flux and also this production flux. These tend to be dominated by these fast propagation reactions, which has trouble picking up the lower flux, chain branching, initiation, and termination reactions. However, we can look if we look at this a little bit differently, and we focus a little bit more on the concentration-driven aspect and sort of the other dimensions of this. I won't go. The paper for this has a lot more analysis of sort of what this sort of algorithm means. But nominally, what we do is we compare our loss flux to our edge flux, the edge contribution to the loss flux for individual species. So what we do, so if we have some edge reaction, we can look at how that edge reaction is going to affect concentrations in the core. And when you run that analysis, you get this sort of branching, this BR number is kind of ends up being the quantity of interest. However, we don't really want to be looking at and trying to get every concentration in the core correct, because that ends up being self-consuming because, okay, we need to add these edge species in to get this concentration right, and now those edge species are in the core, and now we need to get their concentrations right, so we need to add these edge species. And so we add a little bit of a rate ratio flux bias that keeps this under control so that this focuses on getting the concentrations of species that have high throughput fluxes correct. These tolerances are a lot less system dependent, fortunately, and these default values are usually sufficient. I will say that, so the branching algorithm works very well. It's a very general and safe solution, and at least it's a mitigant for even some of the species selection errors that are even harder to deal with. However, in general, when you're running with it, it does tend to cause RMG to only terminate at large mechanism sizes because when you're using it with the flex criterion in concert, they tend to pick up a whole lot of species. And users tend to not like this very much. And it's important in this aspect, educationally, to understand that RMG's termination is not so physically meaningful. Terminating to a specific rate ratio is not a real physical, it does not end up effectively being very physically meaningful. What you really want to care about is trying to converge what you're trying to predict with respect to mechanism size, not making sure your RMG run terminates. And so in that angle, it's that's an important way to look at your RMG run, is to be looking at you don't necessarily need to complete your RMG run. You just need to converge it with respect to what you want to predict. And here you can see in this this test with dodecane pyrolysis, with our model model 2 here uses the branching algorithm, and model 1 and 3 are a couple different variants of the RMG run. But you can see that in many of these cases, we get significant improvements, improved agreement associated with that dashed line here. When using the branching algorithm versus letting RMG run. We also found that it found a lot of species that normally had to be added manually to RMG for RMG to find them. So next, we're going to talk a little bit about transitory edge analysis. So I've talked to you about transitory sensitivities earlier in the sensitivity lecture. You could draw up a scheme for using traditional sensitivities for species selection, but almost anything that you draw up becomes rapidly impractically expensive. Transitory sensitivity analysis, however, as we talked about before, it's time local. It doesn't require any true integrations. So we can apply transitory sensitivity analysis to this core edge system to extract information about the importance of edge species and reactions. And this provides us with a whole ton of detailed information about how these edge reactions and edge species impact individual species in the core. And this is really powerful in the way that it lets us directly kind of select species based on how they affect different aspects or different targets within your simulation. What we have implemented for this is this sort of general tolerance where we compute our transitory sensitivity, and then we take the absolute value and compare that to the maximum transitory sensitivity of all of the other parameters, or the other reactions, sorry. And this allows us to target for individual target species. We can look at how we can essentially ask RMG to select species and reactions that will improve the prediction of the concentration of a given target species. So we give it our interested target species label and the associated tolerance for this equation associated with that. We also set a transitory step period, which is how often RMG, in terms of time steps, RMG runs the transitory edge analysis, because it is significantly more expensive than running the flex analysis or branching analysis. So usually we check it about every 20 time steps in the simulation. And you can do some stuff with this that you could never do with the main RMG algorithm. So if you think about, suppose you were simulating methane combustion and you wanted to predict NOx concentrations. The problem is that the NOx concentrations are really, really small. And so they're going to have really, really small fluxes relative to your methane combustion. Before the transitory edge analysis algorithm, what we would probably have told you to do is, well, you're not going to be able to find that with RMG, so contrive a reactor, some reactor in which just give it a really high NOx concentration, put the species you think should be there, and hope that when you do mechanism generation there, that it will give you a mechanism that gives you the reactions you need to predict NOx accurately. So here, what you can see here is that we run to a relatively low flux tolerance of 0.01, and we barely, between all of these, we only in one case did we even add a nitrogen containing species, and none of these found NO2, starting from just N2 and NO as nitrogen species. However, once we add this transitory NO tolerance, we add lots of nitrogen containing species, because we're driving our species selection to go find reactions that will improve our NO concentration prediction. And so this can allow you to target individual, even trace species in a way that RMG's flex-based algorithm can't really deal with very well without you sort of recontriving a new reactor system to try and deal with it. Now, this is a really intelligent approach for selecting species in RMG. And there's a lot of potential ways it can be leveraged that we haven't really explored to generate mechanisms more reliably and intelligently and converge specific target quantities. However, there's an important asterisk on all of this, and that's the transitory edge analysis can be very expensive. Each step, this requires us to compute this parameter Jacobian, the state vector Jacobian, and this matrix exponential with respect to the core plus edge. So these matrices are the size of our core plus edge scale. For smaller core plus edge, this isn't too bad. This is doable. As long as you're evaluating only every so many time steps, it works pretty well. However, for core edge sizes, I think maybe rule of thumb, core much larger than 300 edge species, as the edge grows, these matrices are going to grow in size quadratically, and mechanism generation is going to rapidly slow down. So this isn't a very good way to build a large mechanism. The other primary species selection challenge is molecular weight growth. So for many systems, take oxidation or pyrolysis, we might start from some starting material that may get a little bit bigger and more complex, like in that feedback loop case I was talking about before, but ultimately it all breaks down into smaller molecules and breaks apart. With most combustion cases, you're just going to get CO2 and you're going to primarily get CO2 and water at the end. However, in other systems, say polymerization or Fischer-Tropsch synthesis, our starting materials are going to become increasingly larger, more complex, and often individually dilute. And as RMG runs in these systems, the flux is going to be diluted between all these possible products. And as a result, we end up with a flux, a large flux across all reactions that are all individually small fluxes, which is very difficult to deal with. It means our flux criterion has to be a lot lower to pick up those diluted fluxes, but it often causes us to find some pathways but miss lots of other pathways in this process. And in general, in reactive species, these radical concentrations tend to end up much higher than they should be because we tend to miss these consumption pathways. Now, the branching algorithm is related to this, and it helps mitigate a lot of these issues. However, because it's flux weighted, as we mentioned before, it's significantly affected by this flux dilution. As we dilute out, it isn't able to help us as much. How I developed this dead-end radical algorithm. And the overall problem to deal with some of these challenges. And the overall problem, if you're looking at an oligomer growth system, is you've got some reactions that are propagation that say add some monomer to some oligomer or something analogous at least, preserving the reactive center. And these reactions tend to be very high flux. However, there's also chain branching reactions that essentially preserve the radical but transfer it to something else and terminate the oligomer, which have kind of medium fluxes, and then these termination and disproportionation reactions that are low flux. It's worth noting that termination and disproportionation, RMG usually doesn't have trouble with these primarily because the radical concentration will simply build up until this flux gets large enough. But in this case, it's very, very dilute. And so it has, because it's so dilute, there's so many possible termination disproportionation reactions. It's hard to find all the ones that you need to bring that radical concentration down. And so when it has all these different possible edge reactions to add, the flux criterion is going to tend to focus on these propagation reactions that are very high flux. And this can cause it to miss some of these chain branching and termination reactions. So the algorithm how I built is based on some of the principles of the branching algorithm, but gets a little bit more complex. Instead essentially working on a way to get rid of that rate ratio contribution to the branching algorithm. And how I did this by focusing on chain transfer, separating these chain transfer reactions and termination reactions. And focusing on the BR, if we looked earlier here, our BR ratio, which was this component over here. These ratios, but only focused on first for these termination reactions, she does it relative to the termination reactions, so not all fluxes. And for this one, it's just the net core. And by doing these separately, she's able to define a tolerance that focuses on these ones separately, that enables her to find a lot of these missing chain transfer and termination reactions and get better predictions on these oligomeric systems. So this is a relatively simple, usually about 0.1 to 0.01 tolerance reaction to core dead end radical in terms of the model block. And how I applied this, she was able to find that this made a very, very significant difference. The branching algorithm, as you can see here, helps a little bit. But Adding in the dead end radical made a very significant difference in bringing down the radical concentration, and also finding finding a lot of these chain transfer and termination reactions. A lot of this content for at least the species selection section is based on this paper here. There's another paper that probably should be here in this PowerPoint that Kei Hong wrote on the pruning algorithms. All right, that's all I've got here. Happy to take questions.
Any questions? We might just need to go and read that paper.
Yeah, I learn every time I see this presentation. Thanks. I think that more of us should be using this than typically do use this.
Yeah,
Again, get the super minimal example from when we first get RMG, we get this minimal example and we put our fuel molecule in and assume that's good. We should not be scared of the complicated things because they're normally there to help us.
Yeah, I think the branching algorithm, I think, is sort of the key sort of general purpose thing here that people should be more familiar with and using more often. Transitory edge analysis is probably for special cases when you have a special advantage of dealing of taking on that complexity.
You said that it doesn't work for very large things or large models, is that?
Yes. Or, well, I mean, it runs for very large models, but it will slow down. The fundamental issue is that the computation for transitory edge analysis scales quadratically with core edge size, whereas for branching and flux analyses, it scales linearly.
If we've got a system where we're trying to discover a pathway to a product that's not there at all yet. So is there anything that will help discover it? I guess it's kind of, as soon as this shows up, everything that helps make more of it, I care about a lot. But if it's not showing up, we can't discover it.
I understand I think, I mean, transitory edge analysis should help you, but you're correct. You do need to have kind of some pathway to what you're looking for. You have to have some starting pathway, because otherwise, if I had to have NO, you have to know what the species is to tell it that you want to get that species right, obviously. But also, if you just had this off somewhere and you didn't have any reactions that made it, then naturally it wouldn't be able to tell. The algorithm's not going to be able to tell much about. I mean, it will be very interested if it finds a reaction that produces it. It will grab that reaction really fast, but it can't guarantee that you'll find those reactions that lead to it.